Hello, I'm Woosung Choi, and I'm a PhD, not PhD candidate. I used to say, I call myself PhD candidate, but I am postdoctoral visiting researcher from South Korea, Korea University. And today I will talk about AMSS-Net, audio manipulation and user-specified source with textual queries. I think another chat, all fine, thank you. So this talk, the title of this talk was from the paper that I submitted to ACM Multimedia. And if you click this link, and then you can find the paper, the original paper. And it was October 2021. And the full title is AMSS-Net, audio manipulation on user-specified source with textual queries. So this is this describes what AMSS-Net can perform. So if you click this link, and then you can check the demonstration files, and some of them I will present here. And this is the API that you can use in Python. So if you have a pre-trained AMSS-Net, and then you can simply modify your audio, like AMSS-Net.manipulate your audio and the text. The text will be just decrease the volume of bass or pan vocals completely to the left side. This kind of operation can be interpreted as a neural network by neural network, and then that neural network, this neural network, can perform some kind of that audio manipulation. So it returns the output here, and this output is similar to this one, the input one, but in this output, the bass will be decreased. The volume of the bass will be decreased. So this is the API of the AMSS-Net, and before moving the details of the AMSS-Net, I think I have to share the motivation that why we started this research. So at that time, I thought it is really difficult for non-expert users to modify their audio files, like including some kind of, for instance, image, audio, video, the kind of multimedia content is really difficult to manipulate. For example, this is the typical example of the multimedia content editing. So for example, it's kind of object removal. So sometimes we want to mute bass or drums in the audio file, but of course, you can do it because you are in the center of the digital music. So you are the expert. So you can use your DAW tools.
If you rotate the laptop,
okay.
I think people can also see you as you are moving around.
Thank you. And I think I have to check cameras. Okay. Oh, still. Okay. So some kind of simple operation is very difficult for users, normal users, So this kind of object removal is also difficult, but when it comes to object level editing, it's much more difficult for them because you have to first decompose it to several components like vocal, drums, and the other, and you have to apply different high pass with different parameters. Like you have to find a medium high pass for vocals, the frequency of the medium high pass for vocals, and then you have to find another parameters for drums, and then apply it separately, and then you have to merge it together to make the output audio. So whatever the tool you use, you have to use that kind of flow. So it will be very difficult, even for you, I guess. The expert of the signal processing, they are also find difficulties when it comes to this kind of job. So that is the motivation I started. I think, how can I hide this? I think the title is that not much that important. Object removal with Photoshop. The title was, sorry. So this is the example of how we can remove the object in here. So we want to remove the balloon here, but with Photoshop, we have to click this link and then follow the one-by-one manipulation guide. But fortunately, we live in the deep learning era, and we can easily remove some unwanted objects like this by masking them. And then we use image painting networks proposed by NVIDIA. And then I think it's too slow. We are still masking it. And we fed this input into the neural network. And then the output, they will be gone like this. Yeah, they are gone. Okay. So this is the application of image painting. This is what was not originally proposed for this kind of operation, but only for image restoration. So they will recover the masked corrupted area by filling plausible contents into this area. But if we intentionally masking some area like this, and then the model will output the plausible image like this with removing the object in here. So it's very convenient. When it comes to considering the interface, the difficulty of the interface, it is much more convenient than this kind of operation. I think this is the another thing is that I read the title for you. So this will be describe what to change. It is the title of this paper. And it is again ACM paper, ACM multimedia paper at 2020. And as you can see here, so this kind of this interface is based on the masking, brushing, and which is more more difficult to use compared to text interfaces. So this is more high level abstract interface that can that we can use. But I'm not trying to say that it is better. So they are pros and cons. They are more abstract and easy to use, but when it comes to the quality of the output, well, it would be better. So I'm not trying to say text, we have to use text. Anyway, so here is racial nagadoms, and another input is text. So textual queries. So male wear a beard, and then racial nagadoms turns into Thor, like very hairy man with mustache. So this paper is describe what to change. As its name implies, you have to describe what to change to describe to change your image. So this kind of interface is very convenient, and this technology will be integrated into the market. So I prepared this slide for this. So they are not in the academic papers. They will be integrated into AI-based image editing tools. And that is why these kind of companies invest their money for this kind to develop these technologies. So I guess the early method was the pix-to-pix. So we have algorithm to extract edge from the input image, like a Sobol operator. So we can apply it to obtain this edge information, and this input and this will be output as for the neural network. So neural network will paint colors into these edges to obtain this beautiful bag. And we can remove what is this? Glasses. Sorry, I'm not good at English. So anyway, we can remove the glasses apart. Remove glasses with kind of masking and image painting. This was from the Edge Connect, and this is what you saw. This is not what describe what to change. This is manipulation again, a text-guided image manipulation technology. So you can change yellow hair and white head. So kind of that kind of text queries will be manipulated, generate this new image. And I think they will be, we can use them sooner or later, like in the future. So, and the same trend came on the audio editing. So this is the example of RX8 from Isotope.
In RX8, we're proud to bring you a completely overhauled music rebalance. Our significantly improved source separation algorithms can divide and conquer sources like vocals, bass, and percussion better than ever. So you can rebalance a master without original stems, even isolate individual elements. So you can rebalance a master without...
This use source separation method based on machine learning. So isotope RX8, this is vocal and bass, percussion, and other. So you can control the volume. And the interesting is that you don't need each stems. So it automatically analyzes the mixture, and then you can control by them, even if you don't have each stem. So it's very interesting. And I prepared for someone, for Jonathan Weiner, but he's absent. So I will skip this slide. So he explains how source separation based on machine learning can be integrated or can be connected into the mastering and mixing. I recommend to watch this, but I think we don't have enough time for it. So the goal of this research was, the first one is I think I should design a neural network that can perform object level manipulation. So why it should be object level manipulation, and then in general we want to edit specific object in the given audio, not the whole mixture. So of course, decrease the volume of the mixture and increase the volume of the mixture. Of course, we can do that very easily, but that is not that we want. So for example, we want to decrease the volume of the drums or vocals or main vocals or guitar, that kind of object level operations. But this kind of specific cases. And more important thing is that we don't have multi-track. Like the example, as I mentioned before, we don't have, for majority of the users, don't have that multi-track. And if we can, the only way is to paying for that multi-track, but it will be not possible because of several issues like copyright. So it is very difficult for them, for non-experts. And the other thing is that easy to use interface. Like it does not have to be a text or natural language like interface, but at that time, I cannot come up with an intuitive interfaces like this in audio. So that is why I choose natural language, not natural language like interface. So this is the same slide, but this defines the AMSS. So audio manipulation on specified source with textual queries is AMSS, and simply AMSS, the abbreviation of it. So this is the demonstration that now I present what AMSS-Net can perform, and this is the original file. First of all, can you hear it? I mean, Zoom people? Yes, and I think we have to increase the volume. Thank you. And you can hear the pianos in the mixture. It's piano. There's two pianos, grand pianos and EP, electric piano. This is, by the way, this is my song. I didn't want to promote it, but just because of the copyright. And if you apply separate vocals, drums, and bass, and the result is there's no piano. So at the beginning, there was piano, but it was gone. And the other operation that it can perform is panning. So that is why I call it multi-channel volume control. I'm sorry. You because panning is also considered as kind of volume control in multi-channel. So the query was pan drum completely to the right side, and I guess we cannot hear it, and people from Zoom cannot hear it. So I recommend it to listen to this sample via the website. But instead, I visualized it. So this is the red one is left channel, and the blue one is the right channel. And this is before and after. So we move the drum to the right side. So the left side will be reduced. The magnitude of the left side will be reduced. And that is why the magnitude of the red one is reduced, because the energy of the drum will be moved into the right side. And again, the other example is pan face to the left side. It's the same thing. So you can reduce the volume, increase the volume, separate or mute, or pan left, pan right. Pan completely to the right means that 0%, 100%. And if you don't use this kind of word, and then 20%, 80%, or vice versa. This use case includes more complex manipulations like DSP. So apply light high pass to drums. So it is much more difficult than simple source separation, because we have to apply DSP or remove DSP from the mixture. This is also my song, but this is the original song. And if we apply light high pass to drums, and then the result, I think it is clear to listen to the snare. There's two snares. That thick snare, that will be very lighter than this. So it will be, it applied a light high pass to the drums. And if you apply heavy high pass to vocals, and then the result is much more clear. And the interesting thing is that it is really challenging to, of course, manipulate some sources is of course challenging, but it is also challenging that preserving the other contents. So it is also challenging because we do not have to, we must not apply high pass to drums if the input queries was like apply high pass to vocals. So we have to preserve the other contents like drums or bass. So that is also very challenging point. So this was the presentation. And before we moving on the real contents of the AMSS-Net, so is there any questions so far? Oh, I spent 20 minutes. So if there is no question, and then I will move on to the next slide. The first, I will define AMSS, the task itself, more formally, and then I briefly introduce the challenges that we encounter to design this network. So, and then I will briefly introduce the architecture of the AMSS-Net and then the experiment. So this is the task definition. So AMSS-Net, for a given audio track A, and there is a description S, it will be a text, and a single AMSS task aims to generate a manipulated audio track A prime. And A prime, the result of A prime should semantically match with this query. So, and the other thing is that, as I mentioned before, so we have to preserve contents in A that are irrelevant to S, that are not mentioned in S. We have to preserve drums if the query is about the vocals. And of course, A has to contain signals from multiple sources like drums and many stems. And S will describe how to manipulate audio signals from a specific sources in A. It could be a single source and it could be a multiple sources. So the title was AMSS versus source separation. So common misunderstanding about this AMSS is that it is just source separation technology. So what is your contribution? But I think that source separation can be viewed as a special case, very specific case of AMSS-Net, and AMSS task is more general concept. So it could be a source separation at the moment, but it does not have to be a source separation. But because reviewers want this kind of table, I prepared this. So of course, ours can separate sources. So this is the performance of AMSS-Net, but it is slightly inferior to the state of the art. So I don't want to explain it in detail, but anyway, at least if we train solely, if we train AMSS-Net solely for source separation with this architecture, without the other tasks like DSP functions and multi-channel panning, and then this performance will be comparable to the state of the art, one of the state of the art, which is most weak one. So we can, they are comparable. But AMSS-Net can perform source separation as well as the other kind of manipulation. And this is what I exactly wanted, the wanted reaction. So sometimes, maybe in the future, we can apply like Siri, a bit more warmth to vocals and makes the guitar tone more brown. So this is the ideal case, and this is why I mentioned it before this slide. But I hope that someday, but unfortunately, the scope of this research is very restrictive for now, because it is really, really difficult to catch the semantic of like brown, the brown tone or brighter tone of the guitar, or more beautiful tone of the vocals. That kind of semantic is very hard for neural network because we don't have data set yet. So this is the scope of the research. So for volume control, there are 4 types of control. So volume control, multi-channel volume control, and filter, low pass and high pass, and delay. But it could be more than that because it has a lot of symbols like apply medium high pass, apply what is the light high pass. What is the opposite of the light? Heavy, thank you. Heavy high pass. So that kind of indicator we can use them to make the problem more difficult. Or as I said before, completely pen left or just pen left. So this is the challenges that we encountered when we developed this model. So the first one is designing the interface itself. So we created a kind of computer programming language like this based on CFG. So to defend ourselves, this is different from natural language. Honestly, we don't need this if you have enough data set, like text data set that describes like your works, like MuseCaps. So if we have a large of data set that describes the music's characteristic, and then we don't need this kind of artificial manipulation language. So we have this full grammar, and computer when training, our trainer automatically generates a kind of text from this probabilistic program context-free grammar to generate a query. Is kind of reverse operation of the parsing, so generating a random text. And the another challenging is data set. We don't have data set to train it directly. So there is no data set directly used for this purpose. So we basically created this data set on the fly using the data set was originally proposed for source separation, like MuseDB 18. So if we have a kind of data set of the triples like A and A prime and S, A was the before and A prime was the after audio, and S is the manipulation text, which is generated by this grammar. And then we can train model like this. So net is the network, and network take the two input, before and description, and it generates A prime hat. And we will compute this loss. So A prime and A prime hat. And by minimizing this loss, we can train a neural network to perform AMSS task. And these kind of triples are randomly generated when training, like this way. So this data set was proposed for source separation. So we all track will be visible for us when training. So vocal, bass, drums, and other source is in here. And if we just take the sum of them, then we can make the input audio. And after we generate S from the grammar, and then we know what we have to do by using DSP or simply muting, masking, that kind of operation. So if the operation was, if the description was apply low pass filter to drums, and then we know we have to apply low pass to drums because we generated it from the grammar. So we select the target and apply DSP function. And we sum vocal, bass, and manipulated drums to make the A prime, the ground truth audio. And now we have A and S and A prime. Now we can train the model to in a supervised manner like this. So yeah, this was the only way that we can use the data set. So we solved the problem by using this method. And another challenging part is usually sound objects are transparent. This kind of characteristic makes this kind of operation more difficult than image editing, because when it comes to image editing, this pixel belongs to a single object. Like this belongs to head of the bird, and this will belong to branch. And you can see me from the zoom. So this part is my clothes. Of course, there is slide behind me, but you can't through me because I am opaque, unlike this audio object. So audio object, while I'm talking, someone riding a bike or something, we can still hear it. We call it noise. So that kind of characteristic, I define it as transparency. So every single moment of the whatever form of the input audio takes, like mixed waveform or mixed spectrogram, if we take the same specific moment, there will be a sum of some sources, the energy of sources or the sample of sources. So that makes AMSS text very difficult. So the thing, in a nutshell, a single object does not only carry information of a single source. So what we want to is apply high pass to vocal, but there is no vocal in our problem. So that is why we cannot use the masking interface, because if you want to make the bird head, like we can mark here, but we cannot mark some to choose vocals here. So that is meaningless. So we cannot do that. And this is not the problem of the interface itself, but also the problem for the network itself. So that is why we came up with this kind of solution. So we assume that we can isolate each sources into different channels like this. So this is the internal representation that we used in AMSS-Net, and each channel they will be treated they will treat a single instrument like this. So the first channel will be bass drum, the second channel will be bass drum, the fourth channel is about the snare drum, and the last channel will be about the female drum. If we can make this representation, and then we can simply mute this by applying masking to mute the snare drum. So this kind of operation is the solution that we proposed for this paper. And this is the, I think we don't have enough time for explaining latent sources, but simply speaking, latent source is more detailed level of the source, which are not described in the data set. So there is no snare drum and bass drum tagged in MuseDB. So there are drums in MuseDB 18, but we can assume that we can use the more detailed level of the sources like this. This is the kind of latent source. And what I will show you is the generated latent sources. So this is the input. I think it's weird because it's my song. Anyway. So this will be generated by mute all the other channels and pick a single channel and generate it with AMSS-Net. And if you listen to this with your headphone in your home without noise, and then it sounds like a drum. And this will be vocals. I can hear it. I can hear it. Sorry.
Maybe it's very low the volume, but I guess it's on.
Anyway, if you listen to this in your home, and then you will find that it can separate such kind of detail level of the sources. So as you can see here, there is no clap snare drums in the data set, and there is no piano in the data set, but it can automatically find such kind of latent sources from the data set. It learns from data set. We does not manually label the latent sources like this is snare drum, this is hi-hat drum, but they automatically learn from the data set. So this is what we did, and conceptually AMSS-Net separates latent sources, extract latent sources, and then manipulate them and then mix them to output the sources, output the A prime. And you can find the details in here if you click this link. And I explained this before, and this is evaluation study. I think there is no such kind of state-of-the-art method before we proposing this model. So we compared AMSS-Net with the other architectures, and this would be the AMSS-Net is very similar to AMSS-Net, which I proposed for source separation, condition source separation, and the result was AMSS-Net outperforms the baseline every time for every task, except for this one, but forgive this because the gap is very ignorable. So 5.65, 5.49. The metric was the MFCC, root mean square of MFCC of the ground truth and the target. So I think the lower value is still good. So the gap is not that significant. And AMSS-Net outperforms in other cases. So this was AMSS-Net. And for the future work, there are several related topics that I want to continue. The first one is self-supervised. This kind of AMSS-Net, the current version, is self-supervised because I guess computer automatically generate the target from the data set. But of course, it is limited. It's not self-supervised. It's more like supervision, not self-supervision. And we can make this another like unsupervised AMSS-Net. Like the flow is like pix to pix. I think this version is really similar to pix to pix that I mentioned before. The connect edge, extract edge from the data set. So computer extract kind of ground truth, not ground truth, but the input, and then use the original data as the ground truth. So this is really similar to pix, but I know it's very limited. The current version is very limited, but it will be expanded to other domains like pix evolved into cyclogen, and it will be evolved into stargen or discogen. So there's a lot of related feature works, and we can apply more complex architecture like transformer, and we can also apply more DFT functions like reverberation, which I failed to model, so or more semantic words like brown tone or lighter tone, and we can apply multimodality like audio sample based editing. So remove this vocal. So you have to record my voice, and if you don't like my voice, and then please remove this ugly voice from this mixture. And you can use video input, like mute the one with the red shirt or black turtleneck. And we can also provide, we can also create a data set for this. And this will be very valuable, I guess. Or we can crowdsource to collect data set from users. And there will be applications like integration with ASL, automatic speech recognition, like Siri, please mute this one, like that kind of operation. But it will be not a research. It will be a kind of applications. So I think that's it for today. So the conclusion is we propose AMSS-Net, and experimental results show that ours outperforms the baseline. And future works, there's a lot of future works that can we can work on. So thank you.